I think this is one of the most remarkable discoveries in stem cell biology in recent times. And all you need to do is look in the literature. There's a paper every week out on this. This is a better way to do it. This is what we're doing. I was visiting a company yesterday in Boston. They're producing kits already to do this. Things are moving very fast, and it's a very exciting time. So now, instead of an embryonic stem cell in the center of this, we can put anyone's iPS cell in the center of this and make these various tissues. And now the goal, and we're doing this currently, is to say, can we take an iPS cell with these same building blocks, if we want, and make an insulin-producing cell? Derek touched on this. One of the issues, of course, of transplantation nowadays with islets is you have two types of immune barriers. One is going from person A to person B, and the second is person B who's receiving the transplant, their own immune system responding to their own cells. The response against the other individual we could overcome with the iPS approach. The challenge we still face, and Derek highlighted this very nicely, is the person's own immune response to what would essentially be their own insulin-producing cells. And that's still a challenge, and it's still being studied in many, many labs. But nevertheless, we have this technology. So what are the next steps in what we're doing? I think we and a number of other groups are doing this, show that these cells really are what we would say insulin-producing cells. Do they sense glucose? Do they respond to glucose? Can we put these in an animal model of diabetes and cure an animal of diabetes? I think that's a huge first step. And can we produce these cells from these new and wonderful induced pluripotential stem cells? I think this is really the cutting edge where we want to be, and I think these are really important next steps. When we think of this model, we think of cell replacement far on the left, but there's a host of other applications to this, and perhaps drug discovery and testing over a second from this side of the board is something we forget a lot about. But the ability to make cells that you can then run through drug testing, drug screens is has enormous potential, very exciting, and has applications to finding new drugs for new ways of making insulin-producing cells, but also for testing existing drugs on whether they destroy or improve the function of newly developed beta cells. So I think there's enormous opportunities. And on this side, models of human disease, if we think there's a genetic component to diabetes, we can make those cells now, and we can start studying what is that, what are the underlying genetic components that would lead to someone having diabetes. We've never been able to do this. Now with iPS technology, we can capture whatever we want. The technology is here. I want to finish with a little bit about what's happening in Toronto. Things are happening very fast. Things are unfolding, not just in Toronto, but just to tell you, we're not far behind. At the McEwen Center, we started a stem cell facility, and the goal of this facility is to take the technology. We can make cell types. We can distribute these cell types to our colleagues within the McEwen Center, the Toronto community at large, and actually the world, given appropriate resources. And this is something that we've started almost a year ago. It's ongoing, and we're up to capacity on cardiomyocytes, and we're just trying to funnel in some of the other technologies. We are partnering with a new initiative, and I'm going to just tell you about that, so we can also deliver the equivalent from iPS cells. And I think this is very important because this technology is moving so fast, and we need to be able to deliver all of these technologies in these different cell types to our colleagues within the community. And this is the Ontario iPS facility. And this is a facility established currently in Sick Children's Hospital in Toronto. But it's an Ontario-wide facility with support from the Ontario government to generate iPS cells for the biomedical community in the province. And we're partnering with them. The idea is they produce the cells, and we provide the technology to turn those cells into different cell types. So I hope I've been able to share with you just a slice of what's happening in Toronto in the McEwen Center. I think it's tremendously exciting times in stem cell biology, be it adult stem cells, embryonic stem cells, or iPS cells. And it's a time, I think, to really get excited about what's happening in the field. What I told you today is happening today. It's not the future. It's happening today. And 2 years ago, I could have never given this talk about iPS cells because they didn't exist. Who knows what's going to happen in the next year? So I think we are at the cutting edge in Toronto, and we want to stay there. So evenings like this, I think, are tremendous, so we can share the information with you, tell you what's happening, and really share our excitement in research with you. So thanks a lot, and I guess we now have question period. Yeah.
Actually, I'll tell you a little story. I'm not really supposed to say this, but when I first met Gordon, when he was first coming here, it was approximately 2 years ago. I asked him the question that all of you want to ask him tonight, which is just give me a date. Tell me when we're ready to have these cells and transplant them into people. And he told me, he said 3 years, and that was 2 years ago. So I'm actually going to hold him to that. So 1 more year and we should be ready. We now have an opportunity for questions, and there are some roving microphones. And if anyone has a question, please put your hand up, and we will bring you a microphone. And perhaps while you're thinking of questions, perhaps ask the first question. I'll ask one question of each of these scientists. So, Derek, there are tons of cells in the pancreas. How do you actually know which is a stem cell? Can you tell us how you identify it?
So at least from adult tissues, there are not clear markers of stem cells, and that's true of any tissue. So blood stem cells, for example, have been known for 50 years, and we still don't have a pure population of blood cells we can identify based on the way they look and the markers they have on the surface. So the best way or the easiest way, I guess, for identifying stem cells is their ability to grow. So the way we isolated pancreatic stem cells from the adult pancreas was, of all the cells in the pancreas, only a very rare cell will divide and make huge colonies of cells. And so it's a retrospective analysis. We know it's a stem cell because it makes huge numbers of other cells. And so and of course, that technology, the ability of a single cell to make large numbers of progeny, provides an opportunity to try and identify markers of the stem cell. So we and others have made some progress, and it turns out that the stem cell in the adult pancreas actually is an immature insulin-producing cell. So it's already producing low levels of insulin. It's not a mature beta cell. It's a subpopulation of the insulin-producing cells that has the ability, apparently, to make new beta cells.
Very interesting. And a question for Gordon. I know that you collaborate, and scientists cannot work in isolation, and it's very important to share your results and collaborate and get ideas from others. Give us a sense of how your group shares your results with others, what mechanism, do you have any bigger groups around the world that you're part of? Can you tell us about that?
Just in response to your comment about the 3 years, I didn't have the job yet, so I was being exceptionally optimistic.
You thought I was on the selection committee.
Yeah. So it's a great question. How do we do this? This does not happen in isolation. We work with people around the world. I'm part of what I think is one of the most spectacular experiments from the National Institutes of Health, and that's an organization that they set up known as the Beta Cell Biology Consortium. And 10 years ago, U.S. Congress put aside $10 million or so to find a cure for type 1 diabetes.